Welcome back, folks. In today's class, I'm going to start with the chapter number 14. And in the chapter number 14, we're going to emphasize on the quantum physics. And before I jump into the quantum physics, I'm going to give you guys some of the formulas which we're going to use in this chapter. So the first formula we're going to use is C equal to lambda times frequency. So C is the speed of light, and lambda is the wavelength of light, and f is the frequency. Now speed of the light, we assume it as constant, 3.00 times 10 raised to the power 8 meter per second, and somewhere you will also find it as 2.98 times 10 raised to the power 8 meters per second. You can use any one of these. It's not going to make a lot of changes to your answer. Now, lambda, as I said, it's a wavelength. Now, all of a sudden, you're going to start asking me the question, how come the lambda came into the picture? How the wavelength, all of a sudden, we started talking about the wavelength. So the answer to that lies into the property of the light. So light has a dual property. Light can behave like a ray. So if this is an object and I'm trying to find what kind of an image is formed in this mirror, as we did in the last chapter, so what we said, that the light travels in a straight line, it strikes the surface of the mirror and then passes through the focal point. Under this, when we were trying to find the image, what kind of an image will be formed, we assumed that the light is traveling in a straight line. And there are certain experiments where we have to assume that light bends from the edges and it travels like a wave. So light, the real answer is that light has a dual property depending upon what kind of an experiment you are performing. Depending upon that, you can assume that light is a ray or a wave. That's the correct answer. Now, another formula we're going to talk about in this chapter is E equal to NHF. And E is the energy associated with the light photon. Energy of a photon. N is the number of photons, and H is the Planck's constant, and F is the frequency. Now, this formula was given by the Planck, and he tried to find out the energy associated with each photon of the light. So basically, what Planck said, that it's more of a light is more of a tiny particles. It's like this, which travels in a straight line, and every tiny particle has some kind of an energy associated with it. So if I wanted to find the energy associated with this tiny particle, it will be equal to ENHF, where f is the frequency of associated with this particular particle. And if we wanted to find the energy associated with all these particles, so I'll count all of them, 1 2 3 4 5 6. So 6 times Planck constant value remains same always, that is 6.63 times 10 raised to the power negative 34 times the frequency value. And frequency value again depends upon what kind of a light we are taking, and depending upon that we can fill in the value, and that's going to give me corresponding energy value. Now, another, I'm going to try and solve one math problems based on this formula. So let's say we are given that we wanted to find out the energy carried by a photon of a red light. So we are given a photon of a red light. So n value will be 1. And it says that energy associated with a photon of a red light which has a wavelength of 600 nanometer. Wavelength of 600 nanometer. Now, nanometer, 1 nanometer is equal to 10 times 10 raised to the power negative 9, not times, 10 raised to the power negative 9 meters. Now, if you're going to use the book, you will find sometimes the book is using this format, 6.00 times 10 raised to the power negative 7 meters. So don't confuse yourself that I told you that it is 10 raised to the power negative 9 and the book is using 10 raised to the power negative 7. So if you see clearly, book is writing it into the scientific form. It is 6.00. So he's moved the decimal 2 places towards the left. That's why it has reduced by 2 points down. So if I were to write, I can write it as 600 times 10 raised to power negative 9 meters, and then I can convert it into the scientific form by moving to the decimal 2 places to the left. That's going to become 6.00 times 10 to the negative 7. So hopefully, now you're not going to be confused with 10 to the negative 7 and 10 to the negative 9. All right, so I wanted to find the energy associated with this photon of the light. So energy value will be equal to NHF, and it is one photon. So N value will be equal to 1, and H value will be equal to 6.63 times 10 raised to power negative 34 multiplied by frequency value. Frequency value, how can I find the frequency? So I just told you the formula, C equal to lambda times frequency, and I wanted to find the frequency value. So C upon lambda equal to frequency. C value, we know that that is 3 times 10 raised to the power 8 meters per second divided by lambda, which is given to me in this case, that is 600 nanometer. So 6.00 times 10 raised to power negative 7 meters. So once you're going to do the math, this number is going to come out to be 5.00 times 10 raised to the power 14. The unit of frequency is hertz, or 1 upon seconds. So this is the value you're going to get. So that value, I'm going to feed it in here. So that's going to be 5.00 times 10 raised to the power 14. And once I'm going to calculate the energy, that will come out to be 3.32 times 10 raised to power negative 19 joules. So that is the energy associated with one photon of a light. Now, so this was a very pretty straightforward and a simple question. Now I'm gonna try and take one more question similar to that. So if, let's say, we are given that there are 500 photons of light, so 500, n value is 500, and wavelength is given to me, which is 510 nanometer, and we wanted to find out what is the uh, minimum energy associated with this number of photons and with this wavelength. So energy value will be equal to, again, NHF. In this case, N value will be 500 multiplied by H value 6.63 times 10 raised to power negative 34, and frequency I can convert it into C upon lambda. So C value is 3.00 times 10 raised to the power 8 divided by frequency, which is, lambda value, which is 5.10 times 10 raised to power negative 7. So once you're going to do the calculation, the value will come out to be 1.95 times 10 raised to the power negative 16 joule. So 500 photons of light with this wavelength carries this much energy. So hopefully you understand how to simplify these questions. Now, let's look into some more complicated problems. And before I jump into the complicated problems, I'm gonna talk about a little bit about the theory of those topics. So Einstein was conducting his experiment, and he he actually established the relationship that light is more of a tiny particles which travel in a straight line. It was initially proposed by Planck, but then Einstein, with his experimental setup, he was able to prove it. So he said that this is how light travels: tiny particles which travel in a straight line. And with this, there was another scientist. His name was Milken, or Millikan, whatever you want to call him. He conducted his experiment, and in his experimental setup, he gave a formula that how you can find out the energy associated with the moving photon which comes out of the surface of any object. So I'm going to first of all basically talk about the Einstein's work, and then I'm going to jump into the Milken's work. So this was kind of a setup which Einstein did. So Einstein splashed a light on a surface. Let's say this is a sodium surface given to me here, And here there is a torch, and from this torch a red light was splashed onto this surface. So what happened was some electrons, none of the electrons actually came out of the surface when he splashed the red light. Then he used some other light, the green light. So after that, he used other colors of the light. With the violet color, or the light which had higher frequency, there was electrons which were emitted out of this surface. Then he was curious to know why the red light or the other forms of the light, why was some specific lights were not able to pluck out the electrons, whereas some of the light rays were able to pluck out the electrons. So he actually concluded that it comes down to the actual frequency or the actual strength of the light. So if I have to give an example for this one, real life example, if you throw a plastic ball onto a surface, what's going to happen? You will find that that ball's going to get bounce back. But if you're going to throw a baseball onto the wall or onto a surface, it's gonna knock out some kind of a paint out of the surface, or it may end up creating a dent. Plastic ball was not able to create a dent because it didn't carry that much energy, whereas the baseball was able to create a dent because it carried that much energy. So that's how he said that every photon, every particle of a light has some specific energy associated with it. You can keep throwing this plastic ball on this surface, but it's not going to knock out any chip. But you once you smash it with the baseball, it will be able to knock out the chip or may be able to create a dent. So that's how he was able to prove that light is a tiny, tiny particle which travels in a straight line. Now, carrying forward his work, Milken gave a formula that how you can calculate the energy associated with the electron which comes out of the surface when the light falls onto it. Let's say this blue light falls onto this, or this violet light, which I'm converting into violet now. So this violet light falls on this surface and it knocks out the electron from this surface. Now this electron, I wanted to find out with what energy this electron will move. So to calculate that, Milken gave the formula. He's basically equated everything. He said that E equal to work function, energy equal to work function plus EKE. And this E is the energy of a photon. He said energy of a photon is equal to work function plus kinetic energy with which the electron will travel. Mark my word, this is energy of a photon. Energy of photon which falls on this surface. So this is a photon which is falling on this surface. This black surface is being struck by the light, and that energy will be equal to work function. What is the work function? Minimum amount of energy required to pluck the electron from the surface. Minimum amount of energy required to pluck electron from the surface. And EK is the energy with which the electron will travel. Energy with which electron will travel. So which electron? The plucked electron. So for example, this energy which is with which it is striking this surface is 10 joules. And minimum amount of energy required to pluck the electron from this surface is 4 joules. So this will become 10 equal to 4, and rest will convert into the kinetic energy with which this electron, which came out of the surface will travel. So 4 plus 6. So that's how you can calculate the energy of the moving electron. So based on this concept, I'm going to take a math problem. So the math problem is that we wanted to find the minimum speed of the electron emitted from the aluminum surface. So this is an aluminum surface, and I wanted to find out the minimum speed of the electron. So once the electron comes out of this surface, what is the speed with which it's going to travel? Once this surface is being struck by or illuminated with the light having a wavelength of 125 nanometer. So the wavelength with which it is struck by is lambda 125 nanometer. So I'm going to strike a light of 125 nanometer on this. And that's going to pluck out an electron from here, and this electron will travel. I wanted to find the speed with which this electron will travel. Now, this is 125 nanometer, so I can find the energy associated with this wavelength, and that value will be equal to E equal to what we've already concluded, that it is NHF. If it is one photon, so then N value will be 1, H value will be equal to 6.63 times 10 raised to the power negative 34 multiplied by frequency. Frequency value we can calculate 3 times 10 raised to the power 8 divided by 1.25 times 10 raised to the power negative 7. And if I do this calculation, that value will be equal to 1.59 times 10 raised to the power negative 18 joules. So this one photon which strikes on this surface, this violet photon which strikes the surface, has this much amount of energy. And then because of this energy, I wanted to find out that the electron which is plucked out, with what velocity that's going to travel. So E is equal to W plus, I'm going to color code it, that will be equal to W plus EKE, kinetic energy. Now this is 1.59 times 10 raised to the power negative 18. Work function value will be given to you in the exam. So it is striking an aluminum surface. That's what I said initially. This surface is aluminum surface. So aluminum work function is equal to, uh, that is equal to, uh, let me figure out, it will be given to you in the exam. So that is 4.08 for this question. 4.08 eV, electron volt. Now this is in joules. I have to convert this value into joules also. So I'll multiply this value with 1.6 times 10 raised to power negative 19. So 1 eV is equal to 1.6 times 10 raised to power negative 19 joules. So 4.08 eV will be equal to 4.08 times 1.6 times 10 raised to power negative 19 joules. That's what the value will be. So thus I multiplied by this number plus EKE, kinetic energy. So whatever calculation you're going to get from here, that will be something like 6.528 times 10 raised to power negative 19 joules plus EKE. And here it is 1.59 times 10 raised to the power negative 18. This is going to go on the other side. 1.59 times 10 raised to the power negative 18 minus 6.528. 6.528 times 10 raised to the power negative 19 equal to EKE. And that value will be 9.384 times 10 raised to the power negative 19 joules, kinetic energy, EKE. and kinetic energy is equal to half mv square, because I wanted to find out the speed with which it's going to travel, half mv square. So 9.384 times 10 raised to the power negative 19, and this 2 is going to go other side. Mass, which mass I'm going to take? I'm going to take the mass of the electron, because electron is coming out of the surface. Remember, that's what I told you initially also when I was writing the formula, electron, kinetic energy of the electron. So I'm going to take the mass of the electron to find the velocity. 1/2 times the mass of the electron is 9.11 times 10 raised to power negative 31 v square. So once you're going to do the calculation, v value will come out to be 1.44 times 10 raised to the power 6 meters per second. So this is the speed with which the electron which is being plucked out of the aluminum surface will travel. So hopefully you understood how you can approach these kind of questions. Now that was the work done by Milken. After that, there was another scientist. His name was Compton. Compton came along. Compton said that the Einstein's work or the Milken's work was, there's a this this was the surface, and then the light fell on the surface, a photon of a light, and it plucked an electron from the surface, and that electron started moving. That's what the work was. But he never talked about what's happening to this photon of the light. So he came up with his own work where he said that, let's say this is a photon of a light, and this is an electron. If this photon strikes this electron off center, then what's going to happen, that the photon's going to end up traveling somewhere in this direction, and electron will travel somewhere in this direction, same as that of the snooker balls or pool balls. So this is going to travel somewhere here, and he actually gave away the formula to calculate the wavelength of deflected light. So this is what? This is a photon of deflected light, of deflected light, isn't it? So this was the initially, when it strikes this electron, it gets deflected. So we can calculate the wavelength of a deflected photon too. So to calculate that, he actually gave the formula change in wavelength. Change in wavelength is equal to delta lambda, which is equal to h upon mc 1 minus cos theta. Cos theta is the angle at which it is getting deflected. And m is the mass of the electron, this electron. There is no mass of photon. Again, no mass of photon. Photon is a massless particle. This photon is a massless particle. So the angle value we can calculate from here, and this mass value is the mass of electron. C is the speed of the light, h is the Planck's constant. Now based on this formula, I'm going to try and simplify one question. So the question is, what is the minimum change in wavelength? What is minimum change in wavelength that a 0.010 nanometer of X-ray photon can undergo by Compton scattering. By Compton scattering. Now we wanted to find out minimum change. Obviously this is with electron, means once it strikes the electron. So what we're trying to find minimum change. So change is delta lambda, which will be equal to h upon mc 1 minus cos theta. That is how we can calculate the change. Delta lambda equal to 6.63 times 10 raised to power negative 34. Mass value is 9.11 times 10 raised to power negative 31. That is the mass of the electron. Multiply by 3.00 times 10 raised to the power 8 and 1 minus cos. Now how I'm going to find the angle? So the angle is hidden in this word minimum. If it is minimum, change in angle is 0 degrees. If it is maximum, if I change the question to maximum, angle will become 180 degree. That's the maximum. So if I see this diagram, this is the minimum change, means it goes through straight away. There is no change and no deflection. And maximum changes, it gets deflected by from where it came from. So 1 minus cos of in this case minimum changes, so 0 degree. So uh, that will be minimum change will be equal to delta lambda, whatever this value is, 1 minus cos 0. Cos 0 is 1, 1 minus 1 is 0. So you're going to keep on calculating this number. Means you can leave this as it is also. I'll tell you why I'm saying you can leave it as it is. 9.11 times 10 raised to the power negative 31 multiplied by 3.00 times 10 raised to the power 8. 1 minus 1 is what? 1 minus 1 is 0. And 0 multiplied by anything is 0. Answer is 0. So minimum change in wavelength is 0. And maximum change, if you were to find out, then you can put the angle as 180 degrees. So this will become negative 1. Cos of 180 degree becomes negative 1. So 1 minus negative 1, that's gonna, you will add up the numbers then in that scenario. 1 minus minus 1 will be 2. So hopefully that makes sense to you guys. So that's about it for chapter number 14. If you can do these questions and some of the problems correspond to these, especially from page number 723, and also from page number 719 and 718, and yeah, that should do for you guys for this chapter. So hopefully you enjoyed this video, and I'll see you with another video. Till then, goodbye.